all to the last lecture of AC/DC load flow analysis. So in this part we are going to consider the fault analysis, that is going to be the faults occurring in the power system, and the transient stability analysis, and the methods that we are going to consider for obtaining the solution of transient stability analysis by considering the various methods. So these are the contents that we are going to cover in this particular lecture, that are the faults occurring. So the faults can be of two types: either it is symmetrical or unsymmetrical faults, the types of these types of faults, then the formulation of sequence impedance matrix, then what is transient stability, what is its importance, the inputs that are going to be required for transient stability, various methods for obtaining the solution of transient stability, and the conditions that we'll be studying in these particular methods. So let us start with the faults. So now in the faults, now the power system, as we know that there is a vast and complex power system in India. So normally a power system should operate under the balanced condition. So till the time the fault is not occurred, the system, we can say it under balanced condition. But the moment the fault is occurring in the system, that causes unbalance in the system, and due to which there this can lead to various types of faults. So this unbalance in the system can be due to failure of insulation at any point, or due to live contact between the two live wires, or a short circuit between the fault. Short circuit is said to occur on any of the transmission line. So fault in the power system occur mainly due to the natural disasters. Usually that can be in the form of lightning, high wind speed, then earthquakes. Other reason is the insulation breakdown, falling of tree, bird, shortening, etc. So major of the faults are occurring on the transmission line, because those are the open part which are passing through the barren land. Other types of the fault like insulation fail, breakdown, or any other fault that is in the substation, those are occurring very rarely. So the faults can be broadly classified into two types. One will be the symmetrical fault, and the second is going to be the unsymmetrical fault. Now let us see quickly what is the symmetrical faults. Now symmetrical fault is the fault where, suppose there is a fault in the system, and the three phases, that is R, Y, B, we consider the three phases, all the three phases will be having the same orientation of the angle. So in these type of faults, all the phases are short circuited with each other and often to the earth. So that is why it can have only two options. So this type of fault is said to be symmetrical. Only the displacement of the angle will be 120 degree apart from each other, and the magnitude will be the same. So it is the most severe type of the fault which has huge amount of currents. So it is the maximum amount of current, and it is, but it occurs very rarely. So that rarely we can consider as 5 to 8%. So for this particular reason, balance short circuit condition is determined by this large amount of current. So typically there are only two types of faults when we say that it is going to be, magnitude is going to be the same for the current magnitude is going to be same for all the three phases. So we have only two types of faults: either triple line fault, that is LLL fault, or triple line to ground fault. You can see in the diagram also the line current is same in RYB. Here it is considered Z, no doubt. So in all the three phases, you can have one horizontal arrow which we can see when the current is said to be flowing. So this is going to contribute to triple line fault, and this is going to contribute to triple line to ground fault. After that we have is the unsymmetrical faults. Now unsymmetrical faults are normal fault, which means that the three phase faults becomes unbalanced. So in this case, if the balanced fault is there, we have said that it is symmetrical fault, but not necessary all the time. These all the three phases will have the same magnitude of current. It will have different magnitude of current also, that will contribute to the unbalanced current. So unbalanced current means unequal currents with unequal phases in the three phase system, and they don't have the same phase displacement. So that is the main difference between the symmetrical and unsymmetrical faults. So the unbalanced load occurs due to the presence of the short circuit or open circuit of the transmission lines or distribution lines. As I've mentioned that most of the faults are occurring on the transmission and distribution network itself. So it is going to contribute to the unsymmetrical fault. So unsymmetrical, there are going to be series and shunt faults. So series fault is between the phase phases or between phase to ground, and the shunt unsymmetrical shunt fault is unbalanced in the line impedance. So there it can be divided into two, series and shunt. So it can be occurred by natural disturbances or by manual errors. The natural disturbances may be heavy wind speed, ice loading in the ice falling countries, lightning strokes, and other natural disasters. So here, the types of unsymmetrical faults, we are going to consider the line to ground, line to line, double line to ground. So these three faults we are going to consider. So single line to ground is the most common occurring fault because it occurs only on one phase out of the three phases with respect to ground. So one conductor comes in contact with the ground or the neutral conductor. So single line to ground is the most frequent occurring fault, that is 60 to 75% of occurrence. So that is going to be the major contribution. It is we can say it is the most occurring fault in the power system. Second is the line to line fault. A line to line fault occurs when the two conductors are short circuited. So in this type of fault is in the range of 5 to 15%. Now this is the probability or the percentage contribution to the fault which can occur in the power system. Third type is the double line to ground fault. A double line to ground fault occurs when two conductors fall on the ground or come in contact with the neutral conductor. So this is very important. So this contributes to 15 to 25% of the occurrence. So these are the two types that we have considered, symmetrical and unsymmetrical. So if we compare symmetrical and unsymmetrical, in unsymmetrical fault, the contribution, or it is the most occurring, it is not much severe, but it is the most frequent or occurring fault in the power system rather compared to the symmetrical faults. Now let us go to the formulation of sequence impedance matrix. As we have seen in the unsymmetrical fault, that the shunt, there will be the problem in the shunt, or we can say unsymmetrical shunt fault occurs because of the change in the line impedance. So this will help for the calculation point of view, that how to do the formulation of sequence impedance matrix. So we can have either, suppose we consider a balanced star impedance load. So the impedance of each phase, we can see that here the phases I have considered now in terms of A, B and C. So this is for just for the notation that I have considered. So you can see that the each has the impedance ZY, ZY and ZY. So this ZY is going to be resistance and reactance for all the three phases, and the neutral impedance is going to be denoted by Zn, where it also has a resistance and reactance. So the current flowing through each phase, we can see it is IA, this is going to be IC, and this is going to be the neutral current. So VAG is going to be the voltage with respect to this, we can call it as phase voltage with respect to ground, this phase voltage with respect to ground, and the third phase voltage with respect to ground. So, and all this, we can say that it is earth, neutral is earth through certain impedance. That impedance we are taking it as Zn. Now from this figure we can see that VAG, we can obtain the equation which is given by Z into Y. Z into I, so we can have ZYIA, so that is ZY is going to be the impedance which is going to be for the particular phase into the current IA. Then we have Zn into In, that is flowing through the neutral. So neutral current is nothing but the total current. Neutral current is the total current which is coming from IA, IB and IC, because all these three are incoming and this is going to be outgoing. So by simple KCL we can say that we have replaced this by this quantity. When you open the bracket we get this particular equation. So similarly on the phase B and C we get this kind of equation. Now when we represent this in the matrix form, so this becomes VAB, VBG, VCG. So we have now ZY plus ZN, ZY plus ZN, ZY plus ZN. So diagonal elements are same, the off diagonal elements are different. This is due to the reason that the impedance we have considered similar for all the three phases multiplied by the current vector IA, IB, IC. So this we can say VP equal to ZP into IP. Now VP will be the line to ground voltage, IP is the phase current, and ZP is the 3x3 phase impedance matrix that we have considered for the three phase system. So those equations can be used to determine the value of the sequence voltage currents. Now we multiply with a pre-multiplying factor, that is A into Vs, to this particular equation equal to ZP A into Is. Now this A is this primary, whatever is there, the phase voltage, we are considering it into the some other parameter. in terms of Vs, we can say. So pre-multiplying now by A inverse, A into A inverse becomes identity matrix. So this becomes Vs equal to A inverse ZP A into I. So this A into A inverse again becomes I. So now this becomes Vs equal to Zs into I. So same like this particular equation that is on the primary. This is on the secondary. So where Zs will be A inverse Zp into A. So the impedance matrix Zs is called the sequence impedance matrix. So this is by the definition of A, its inverse AP and ZP. We can obtain this sequence impedance matrix in terms of the operator that we have, A operator that we consider for positive, negative, and zero sequence. Now this positive, negative, and zero sequence, it is already covered in the previous semester power system analysis course. So that is why we are not considering here the derivation part. So we are having this operator multiplying matrix, that is 1/3 because three phases are there, and this is going to be the symmetric matrix. The rows can be transformed to column. So we can have this multiplied by this, and after that we are going to have again the same factor, only this will be A inverse. So this is going to be the A matrix which we have represented here, and this is going to be the A inverse matrix. So we know that identity 1 plus A square is 0. So when we substitute here, we have to multiply this particular matrix. This and this matrix is multiplied, we get this matrix, and then when we multiply this matrix, we get this overall matrix. So if you observe that this is going to be a sparse matrix where most of the off diagonal elements are 0. So more the number of 0 elements are there, we call it as a sparse matrix. Only the diagonal elements are non-zero. This is very important to note down. So the sequence impedance matrix is always a diagonal matrix which have three uncoupled equation, as I have mentioned. Now when we multiply this equation with this particular matrix, we get three separate equation. V naught I naught will be equal to zy plus 3zn into I naught z naught I naught. V1 will be z1 I1, V2 will be z2 I2. Note down this V naught V1 and V2 are represents zero sequence current, positive sequence current, and negative sequence current respectively. So that is what we get, this zero sequence impedance, positive sequence impedance, and negative sequence impedance respectively. So that is very important. Now let us go to the transient stability analysis. So that was the part of the fault analysis. So importance of transient stability. So the goal of the transient stability is to analyze the stability of the power system from sub-second to several tens of seconds. Now we know that whenever there is a fault occurring in the system, the moment the fault has occurred, we can say the system is under stable condition for few seconds. We have to recover the system back to the stability to avoid the system going into much more in the transient stability. So the stability is very important, as it is the operating condition being exposed to the disturbance such as tree falling or bird sitting, or there is a bird shortening or ice loading. Automatic disconnection of that line is to be done in order to protect the other parts of the system. That means we can say that the system should remain healthy. Whatever is the unhealthy part, or whoever is creating problem or stability, we have to separate it out from the healthy system. So in electrical engineering terms, we say that the power system is stable if the substation voltage level and the rotational speed of the motors generators return to their normal value in a quick and continuous manner. That is going to be there with the help of the protective devices. So the protective device, relays, and circuit breaker coordination should be very much have a very much important role to play over here to bring back the system to normal state. So the inputs that we are going to consider for the transient stability are, the transient stability is going to require a very much input. So that is the number, size, and types of the generator which are available, mechanical, electrical parameters. So location and specification, the fact devices, static VR compensation, location and specification of protective devices, load shedding, location, and other control protective devices. So the amount of the time it takes grid voltages to return back to their intended level is dependent upon the magnitude of voltage disturbance. So if the voltage disturbance is well within the limits is there is very less disturbance, so it would takes very less time to cover back to the system. If the system is not brought back to the normal state, then it will go into some other states of the power system. Now let us see quickly the few methods that we have to consider for the solution of transient stability. So here we are going to discuss about the three methods, that is the Euler's method, modified Euler's method, and RK method, that is Runge-Kutta method, for obtaining the solution of transient stability. So Euler's method, so all these three methods are applicable to find the solution of non-linear equation, that is non-linear differential equations. So these methods are beneficial for differential equations. So let us consider a non-linear differential function dx by dt which is equal to fx exists, and we can say that the Euler's function is applied to this 2-inch time instant t0 and tf. So the first iteration can be calculated. You can see here x1, it will be equal to x0 plus derivative of dx by dt multiplied by delta t. So x1 is the variable which is time constant, which is depending on t equal to t0 plus delta t. So this process is repeated until the final time tf is reached. So we can have the number of division into various points, and that points can be calculated. Note down the this is expansion is nothing but it is the Taylor series expansion that we have studied in mathematics part, engineering mathematics, and neglecting the higher order terms because the derivative will go on increasing, and that is contributing to very less amount of deviation. That is why we are neglecting that higher order terms. Also, there may be chances that they may introduce error. That is why we are reducing that. So, and then in modified Euler's method, what we have is the predictor and corrector steps. So this is nothing but the predictor and corrector steps, which we call it as in Euler's method, that is the modified Euler's method that we will be studying in the upcoming slide itself. So note down that this k plus 1 and k is only going to be the iteration that we are performing with the help of this prediction and corrected value. So that is going to be the main importance. So ideally delta t should be equal to 0, that is the difference between the initial and the final value should be 0. But as we know that we are starting with the initial approximation, so there will be some variation in the approximate and the exact solution. So we can see here the difference between the two. We have seen the T0 and TF, we are dividing into 3 points, first point, second point, and third point. And this is the exact solution, and this is the approximate solution. So there will be a slope. This delta T will represent the difference, that is in the terms of x and y coordinates, that will represent the slope. And that slope is very important. That is what it is mentioned, the slope or the difference between the two values, consecutive values, should be 0 in order to avoid this deflection or the deviation between exact solution and the approximate solution. So let us see how it is applicable for swing equations. We assume the initial condition omega naught equal to 0, del naught equal to del initial, and PA, this is the power output that we are getting, accelerated power we are getting as mechanical power minus maximum power into sine delta. Now this is the part of the derivation we have obtained from swing equation. We are not going into derivation of swing equation because it is also covered in power system analysis course. So for nth iteration of Euler's method, we are applying this particular step. Omega naught becomes omega n minus 1 plus delta t 1 by m PA del n minus 1. And del n will be equal to del n minus 1 plus omega n del t. So this is going to be applicable for obtaining the solution of swing equation. So this we have now. Please note here this omega is the angle rotation speed for that particular shaft. So for solving the modified Euler's method, we have these notations that we have considered from the swing equation. So when we use this sequence, operation takes place for omega p will be equal to omega plus delta t 1 by m PA delta, and delta p becomes equal to del plus omega p delta t. So this we get the predicted value of the function, which can be applied for corrected formula also. We can omit the step d omega by dt in order to know the value of omega p. So then after this predicted value, when we can go for corrected value, which the formula we have seen, just we have to substitute the values from the omega and omega p values. Similarly for delta, del values, del and del p, we can get the corrected value. So these are the two methods or the two simplifying methods that we can apply for obtaining the solution of the Euler's method. Now in modified Euler's method, what we are going to do is, in the predicted and corrected value itself, we have seen that that is representing the modified formula. Yes, it is done so. So the main part of the transient stability is the load flow calculation. Now we have seen in the load flow studies that in the previous lecture also that load flow studies is helpful for predicting the transient stability. Now it is helpful not as it is that it is depending on the load flow equation. Only few conditions we are considering from the load flow calculation to before the fault occurs. So whenever there is a fault or there are certain changes in the power on the real time basis, we can do the calculation using optimal power flow analysis, and considering those values we can just predict whether the system will be going into the fault or not prior the system has gone into fault. So that can be considered in the planning stage, considering the historical data we have. So in power system it is important to solve the first order differential equation for few or two for every machine to get the alterations in both voltage angle and the machine speed. So this voltage angle d theta by dt is omega it minus 2 pi f, and the machine speed d omega t by dt will be equal to pi f by hi pmi minus pet, where I will be equal to 1, 2, 3 up to m. That is the number of machines. M will be representing the number of machines. So if we are having m machines, there will be two equations. Two m equations. So one will be contributing to the voltage angle, and the other will be contributing to the machine speed. So by assuming the governor action negligible and the other power losses to be power generated power to be constant, then the modified Euler's method can be applied for voltage angle and machine speed by considering t plus delta t. Now just we have discussed what is delta t, that is going to be the difference between the initial and final value. So this should be minimum as possible. So theta I naught we can consider for first iteration considering this value and the previous value. So this is the new value which we have to obtain, and this is the old value, derivative of old value with respect to t into delta t. So these two equations we can apply for obtaining the voltage angle and the machine speed. So now to obtain the second value, that was the first value. Now to obtain the second value, we should consider the derivative of time t plus delta t to be evaluated. So this demand determines the initial values of the machine powers at the time t plus delta t. So the new components of the internal voltage will be now ei t plus delta t naught will be equal to ei cos theta I t plus delta t naught. So this is going to be the for the voltage, and this is going to be the f term that is going to be related to the frequency that we will consider for considering the sine of the angle. So these two equations are same, only the difference is between the sine and cos. So to get the solution of the network, the voltage and the at the internal machine buses should be fixed. Now what mean by fixed? This is fixed means by when it is fixed, then only we can obtain the solution. If suppose at the fault cases for the three phase fault, the voltage En is fixed to 0. So in that case, what will happen is the terminal current can be calculated by using this relation, which we can see I naught will be equal to E naught minus E naught. That is for this is T plus delta T. This is also T plus delta T. This is going to be E dash, and this is going to be E into 1 upon the reactance or the impedance that we are having during that particular calculation. So the total power can be calculated, which is going to be the real part of the product of voltage and current, that is we can obtain these particular values. So the second values of both the machine and angles can be calculated by using these steps. Now in the second case, we can see that it is iteration number 1. Earlier it was 0, now it is 1. So this is going to be the new value, this is going to be the old value which we have obtained from the previous iteration. Also note down the difference, we are taking the average of the two derivatives multiplied by delta t. The same thing is applicable for the machine angle. This is the first order derivative which is already discussed in the previous slide. So these equations can be performed. So this procedure is repeated until the maximum torque is obtained, whatever is satisfied. Until and unless we obtain that torque, we have to go on proceeding with the equation. Now what is the importance of this modified Euler's method is for calculating the transient stability of power analysis, power systems, and the behavior of the machine and the performance of the system, whether the maximum torque is obtained or not. Through the help of the swing equation, we can check the stability of the system also, the inertia that should be there in the for the generators, motors, etc. So the solution is evaluated by a series of estimated for internal machine bus and the machine speed at the next step, and repeating this operation allows evaluating the line currents and the swinging impedance for the pre-selected line. So this will be very beneficial that we should take preventive measures at the planning stage itself so that these transient conditions can be avoided. So the other method which we have is the RK method. So Runge-Kutta method, we consider the fourth order approximation. We have second order, third order, and fourth order, out of which we consider only the fourth order for this power system analysis. So in the we can see the changes in the internal voltage angles and machine speed for the simplified machine presentation. The formula which we can see as delta del 1/6 k. So there are four terms, k1, k2, k3, k4. So this k terms are going to represent, there are four terms, that is why it is called as fourth order approximation. So this is for voltage angle and this is for machine speed. So if there are n number of generators, we can obtain for all values, and k's and i's are nothing but the values obtained from the derivatives of the predetermined points. So this procedure is going to be obtained for solving the equation 4 times. Now let us go through quickly through the algorithm of AC/DC transient stability. Now as we have seen that for HVDC link, when we consider the stability assessment is carried out taking into account the power constraints, then the synchronous AC system DC link is considered, which will apply at the different nodes considering the converter constraints. So the steps for transient stability. So initial, we consider the bus voltage for is from the AC/DC load flow before the disturbance. After the load flow is obtained, the machine currents and voltage behind the transient reactance are calculated. The machine speed is equated. The mechanical power can be calculated with the help of this same equation. The network data is modified, whatever the extra nodes are there, or admittance matrix is considered for the load, and we are going to set the initial time t equal to 0. So during the switching operation or in any fault condition, network data is to be modified as per the load flow condition, because at the time of switching there is going to be the change in the power flow that we have to calculate. So the machine differential equation can be solved with the help of Runge-Kutta method to obtain the changes in the internal voltage and the machine speed. The internal voltage angle and the machine speed are to be obtained and stored for plotting. So AC/DC load flow is performed again to get the new output of the machines, and then after calculating these values, then we are going to have the time change, that is going to be t plus delta t. Check for the limit convergence for time if it is within the maximum limit. Repeat the procedure from step 6, which we can see here after for the switching operation. If else, plot the graphs of the internal voltage angle and the machine speed and stop the process. So from that graph we can calculate the transient stability. So that's it for this particular lecture. In the next lecture we will start with the optimal power flow analysis, its introductory part, and the steps that can be, or the methods that can be applied for the optimal power flow analysis. Thank you.